Hello everyone, my name is Wei-Tian Wang. Today I will present our work, HTTM headwise temporal token merging for faster VGGT. The core question is simple. Can we make VGGT much faster on long multi-view inputs without retraining and without sacrificing reconstruction quality? Let me start with the motivation. VGGT is a recent feed-forward 3D reconstruction model. Given a set of views, it directly predicts key 3D attributes, including camera parameters, point maps, depth maps, and point tracks. A key design is the alternation between frame attention and global attention. Frame attention works within each image, but global attention lets all tokens from all frames interact. This is powerful but very expensive. With 80 views at 518 resolution, we already have more than 100,000 tokens, so the global attention layers become the main latency bottleneck. One general way to reduce the inference cost of transformers is token merging. The idea introduced by Tommy is to find similar tokens and replace them by a smaller number of merged tokens. This is training-free and can be applied to existing models. For VGGT, token merging is attractive because many tokens are spatially or temporally redundant, so we may reduce the sequence length before expensive global attention. Fast VGGT already applies this idea to VGGT. It globally computes token similarity across all tokens in the global attention layer, merges many of them, and obtains large flop reductions. However, the matching itself is expensive because it still compares tokens globally. When the sequence has more than 100,000 tokens, computing a global similarity matrix becomes a major overhead. This leads to our main insight. Fast VGGT reduces the attention cost, but the matching cost scales quadratically with the number of tokens. So we ask, do we really need to compare every token with every other token? If the similarity map has a pattern, maybe we can restrict matching to a much smaller region while still keeping most useful matches. Here is the pattern we observe. The x and y-axes are token indices, and the value is cosine similarity between different tokens. High values near the main diagonal mean nearby spatial tokens are similar. The repeated off-diagonal bands correspond to nearby frames, meaning that tokens from corresponding image regions across adjacent frames are also similar. This tells us that useful matches are not arbitrary. They are concentrated in local spatial neighborhoods and temporally corresponding regions. With the insight and observations in mind, let's now go through our contributions. Our first contribution is blockwise token merging with temporal reordering. If we naively split the original token sequence into local blocks, we reduce matching from quadratic to linear, but the blocks mainly capture spatial similarity and miss temporal correspondence. We therefore reorder tokens before merging. We stack spatial blocks from consecutive frames together to form temporal merging blocks. In this way, within each block, tokens are likely to be similar both spatially and temporally. This preserves merging quality while reducing the matching cost by about 80%. The second contribution is headwise token merging. Existing token merging methods usually share the same merge topology across all attention heads. After unmerging and concatenation, this can create repetitive token chunks and reduce representational diversity. In HTTM, each attention head performs merging independently, using its own similarity pattern. Different heads can therefore preserve different information, and the final concatenated embedding keeps more token uniqueness. The third contribution is adaptive outlier filtering. Temporal reordering is useful, but not every block is equally safe to merge. Some blocks or some heads contain tokens that are far from their merged centroid. We first compute the distance from each original token to its merged token. Then, under a global budget, we mark the top distance tokens across all heads as outliers. These outliers are not merged, and their contributions are removed from the centroid. This compensates for difficult blocks and sensitive heads while keeping a fixed merging ratio for efficient implementation. Now let us look at the results. On long sequences, HTTM gives up to 7 times acceleration compared with standard VGGT at 1000 frames. Compared with fast VGGT, HTTM achieves much better latency on long sequences while maintaining comparable reconstruction performance on 7-scenes dataset. On nRGBD dataset, HTTM achieves better accuracy and completeness than fast VGGT at higher merging ratios due to the headwise merging design. Finally, let's take a look at the qualitative results. Compared with fast VGGT, HTTM better preserves fine geometry and local details, as headwise merging avoids feature collapse and outlier filtering protects tokens that should not be merged. To summarize, HTTM is a training-free acceleration method for VGGT. It exploits VGGT's spatial and temporal token similarity, reduces matching overhead, preserves head-level diversity, and achieves strong speedups with negligible quality loss. Thank you for listening, and feel free to reach out to us for any questions.